Artificial intelligence has undergone a dramatic transformation over the past few decades. What once started as a field dominated by rule-based systems has evolved into a dynamic domain driven by machine learning and deep learning models. The shift from explicitly programmed logic to data-driven adaptability has not only changed how machines process information, but has fundamentally redefined what it means for machines to be intelligent. In the early days of AI, systems were built using rules. If-then statements created by human programmers to define behavior. These expert systems aimed to replicate decision-making by encoding the knowledge of human specialists into vast libraries of logical statements. For example, in a medical diagnosis system, developers might input hundreds or thousands of rules, such as if the patient has a fever and a sore throat, then consider strep throat. These systems were deterministic and transparent. Developers could trace exactly why a decision was made, and errors could often be corrected by adjusting the rules. These rule-based systems thrived in narrow domains, where logic could be exhaustively defined. Early successes like mycin, a system for diagnosing bacterial infections, demonstrated that with enough rules, machines could match or even outperform human experts in specific tasks. However, the limitations of this approach soon became clear. Real-world environments are messy, uncertain, and ever-changing. No rule set, no matter how exhaustive, could capture the infinite nuance of language, perception, or human behavior. Moreover, rule-based systems struggled with scalability. Adding more rules increased complexity and made systems harder to maintain. Conflicts between rules could lead to unpredictable results. And most critically, these systems lacked the ability to learn from data. They couldn't adapt to new information unless a human explicitly reprogrammed them. This rigidity proved to be a bottleneck. Enter machine learning, a paradigm shift that changed everything. Instead of programming intelligence directly, developers began training machines to learn from data. Rather than feeding in rules, they fed in examples. For instance, instead of telling a system every condition under which a tumor might be malignant, they provided thousands of labeled medical images. The system learned patterns from the data itself, building probabilistic models that could generalize to new unseen cases. This approach unlocked a new era in AI. Algorithms such as decision trees, support vector machines, and neural networks began outperforming rule-based systems in complex tasks like image recognition, speech processing, and natural language understanding. The key difference was that machine learning systems could improve over time. The more data they received, the better they became, learning hidden correlations and adapting to new domains with minimal human intervention. The breakthrough accelerated with the rise of deep learning. Inspired by the human brain, deep learning models use multiple layers of artificial neurons to process and transform data. These models can capture complex abstraction, detecting faces in photographs, translating languages, even generating human-like text. Tools like convolutional neural networks, CNNs, and recurrent neural networks, RNNs, expanded the frontier of what AI could achieve. With this evolution, the role of human engineers changed. Instead of encoding knowledge directly, they began focusing on designing architectures, curating datasets, and tuning parameters. In a sense, they stepped back, allowing data and computation to drive the learning process. AI became less about rigid instruction and more about flexible inference. But the shift also introduced new challenges. While rule-based systems were transparent, learning-based systems often operate as black boxes. Their inner workings are complex and difficult to interpret. When a neural network misclassifies a tumor or generates biased predictions, it's not always clear why. This opacity raises concerns about accountability, trust, and ethics. To address these concerns, researchers have begun exploring interpretability tools and explainable AI, XAI techniques. These methods aim to shed light on how models make decisions, whether through attention heat maps in image classification or saliency mapping in language models. The goal is to balance the power of learning-based systems with the clarity once provided by rules. Another crucial difference between rule-based and learning-based AI lies in data dependency. Rule-based systems required domain experts. Learning-based systems require vast data sets. In many ways, data has become the new source code. The quality, diversity, and bias of training data significantly influence outcomes. If biased data is fed into a model, biased decisions will come out. This has led to a new focus on dataset curation, fairness auditing, and data governance, areas that were less emphasized into. Furthermore, the scalability of learning-based systems has far surpassed what rule-based systems could achieve. Modern AI models like GPT-4, Gemini, and Claude operate with hundreds of billions of parameters trained on massive corpora of text and multimedia. These models perform tasks that would be unfathomable to early rule-based designers, from composing music to writing code to engaging in nuanced conversations. Yet, some critics argue that the pendulum may have swung too far. In our quest for scale, we may have overlooked simplicity, causality, and symbolic reasoning. Rule-based systems, for all their flaws, offered clarity and control. Some researchers are now investigating neuro-symbolic approaches, hybrid systems that combine the strengths of both paradigms. These systems aim to blend the learning ability of neural networks with the logical rigor of symbolic reasoning, allowing AI to both adapt and explain. There is also growing interest in few-shot and zero-shot learning, techniques that allow AI systems to perform new tasks with minimal or no examples. This is a stark contrast to earlier models that required massive retraining for each new domain. Such advancements point to a future where AI may become more general, more versatile, and perhaps closer to human-like learning. The evolution from rule-based to learning-based systems also mirrors a broader trend in computer science: the shift from explicit programming to emergent behavior. As systems become more complex, we rely less on telling them exactly what to do, and more on creating environments where they learn what to do. This opens up incredible potential, but also requires a new mindset for engineers, policymakers, and the public. Education, too, must evolve. Training the next generation of AI practitioners involves not just teaching programming and math, but also ethics, sociology, and communication. Because the decisions made by learning-based systems impact real lives through hiring algorithms, medical diagnoses, and legal assessments. It's important to remember that rule-based and learning-based AI are not mutually exclusive. Each has strengths and weaknesses. In safety-critical applications like avionics or nuclear systems, rule-based logic still prevails. In dynamic environments like social media or e-commerce, learning-based models excel. The key is not to discard one for the other, but to understand where each fits best. That this nuanced understanding is what will shape the next wave of AI systems. Not just smarter, but also more responsible, more transparent, and more aligned with human values. Looking ahead, the line between rule-based and learning-based systems may continue to blur. We may see systems that start with learned models but refine their behavior through rule-based overlays for safety, or systems that learn not just from data, but from structured knowledge graphs and logical frameworks. The future of AI might not be a choice between rules or learning, but a synergy, where knowledge is codified when appropriate and inferred when necessary. Just as the human brain combines instinct with logic, emotion with experience, AI too may grow into a hybrid intelligence. Ultimately, this journey reflects our evolving understanding of intelligence itself. At first, we thought it could be reduced to rules. Then, we discovered it could emerge from data. Now, we realize it's a balance of both and more. As we continue to build machines that learn, reason, and adapt, we are also learning more about ourselves, our biases, our complexity, and our capacity to teach. The evolution of AI from rule-based to learning-based systems is not just a technological milestone, it is a philosophical one. It challenges us to reconsider how knowledge is defined, how decisions are made, and how power is distributed in a digital world. As we stand on the threshold of ever more capable AI, one truth remains. How we train these systems and what we teach them will define their future and ours. In the end, the evolution of AI is also the evolution of how we, as a society, choose to encode wisdom into technology. Not by dictating every rule, but by enabling learning that respects human values.